In the early days of flight, engineers relied on building materials like wood and canvas to build their planes. The Wright brothers worked tirelessly to reduce the weight of their aircraft to allow it to get off the ground. They used woods with high strength to weight ratios like spruce and ash to build their frame, but it needed to be reinforced with steel wire to prevent the frame from bending under flight loads. The flight surfaces were covered in lightweight fabric to provide a smooth aerodynamic surface, but one of their greatest innovations was the construction of their engine. No engine existed at this time that matched their power to weight requirements, so they went about inventing their own. They were the first in history to use aluminium as a building material for an engine, using it to construct their crankcase. They even painted the engine black so their competitors couldn't see the engine was built with aluminium. Aluminium makes up 8% of the Earth's crust. Despite that, it used to be one of the world's most expensive materials. It is a difficult material to refine. Napoleon had envisioned the lightweight metal as the perfect material for weapons and armour, but became frustrated with the difficulty of the refining process. Finally giving up, he had a small supply of aluminium melted down and made into cutlery and plates to serve his most esteemed guests, while the lower ranks were resigned to the less expensive gold pieces. It wasn't until the 1880s that methods capable of mass producing the material were developed. In a few short years, aluminium went from being the most expensive metal on Earth to one of the cheapest, dropping in price from $1,200 per kilo in 1852 to just $1 per kilo at the start of the 20th century. This paved the way for the Wright brothers to use the material in the Wright Flyer, but the material the Wrights used was very different to the aluminium alloys we see today. Despite the availability of aluminium, planes throughout World War I continued to use wood and canvas as their primary building materials because the aluminium that was available back then was weak and malleable. An accidental discovery of a new heat treatment by the German scientist Alfred Wilm led to the development of an aluminium alloy strong enough for structural use. Alfred was trying to recreate the effects of quench hardening that is seen with iron alloys like steel. You see this process a lot in the Awesome Man at Arms series. After heating the steel between 700 and 900 degrees, they'll quench the blade in oil or water. This rapidly cools the steel, which causes a crystalline structure called martensite to form, which is much stronger than the crystal structure that would form if it was allowed to cool slowly. But this technique does not work with aluminium. As the story goes, one Friday afternoon, Alfred was testing a new alloy of aluminium he had developed containing about 4% copper. He followed the steps for quench hardening. He heated the metal up and allowed the heat to evenly distribute throughout the material. He then removed the metal from the heat and quenched it, rapidly cooling it. He then tested the material, but it showed no real sign of improvement. Becoming frustrated, he left the lab, leaving the remaining samples resting at room temperature over the weekend. To his amazement, when he returned the following Monday, he discovered the remaining samples had grown stronger. Alfred Wilm had just accidentally discovered age hardening, a process that would make aluminium the world's new wonder material. So what happened here? Why did the alloy get stronger over time? To understand this, we need to look at the metal's crystalline structure. This is a single aluminium atom. Now, if it's joined by more atoms, they don't just arrange randomly, they form irregular patterns with a repeating structure. Aluminium forms a repeating crystal structure called face-centered cubic, which looks like this, and it defines many of the properties of the material. One of these properties is the direction it most easily deforms. For example, this crystal structure deforms most easily along this plane. This is called a slip plane. Let's look at a 2D cubic structure like this. It can easily slip in these parallel directions, so if a force is applied here with sufficient force, each atom will shift down and the material will be permanently deformed. But this material is pure aluminium. What happens when we swap some of these aluminium atoms for copper? Copper atoms are slightly larger than aluminium, and they create internal strain when fitting into the aluminium crystal lattice. When the alloy was heated, the copper spread evenly through the material, and the quenching process trapped the copper in these locations. In these positions, the copper atoms do not provide much strength, but over time, they will begin to coalesce to form these secondary crystal structures within the main crystal structure. This is called a second phase. These second phase particles create barriers to deformation. For deformation to occur, a much greater force is needed. In the following years, Alfred perfected this process, figuring out the ideal aging temperature and time. He dubbed this new material duralumin, and it was used to build the world's first all-metal aircraft, the Junkers J-1. The impact this age-hardened aluminium had cannot be understated. It completely transformed our world. Prior to its introduction, plane frames were all built with rigid truss structures like this. With aluminium at their disposal, engineers could create a new flight structure, the monocoque and semi-monocoque. With these frames, the aluminium skin forms an integral part of the plane's strength, not just being used as a streamlined flight surface. These new techniques freed up space within the planes and allowed spacious passenger planes to be developed, ushering in a new era of travel in the world. 13% of the world's aluminium is used by the energy sector. Even though copper is a better conductor, All main overhead power lines use aluminium as the conducting material. To carry the same current as a copper wire, an aluminium wire needs to be 1.5 times thicker, and even then, it is still 2 times lighter. This decreases the load on pylons and allows the spans between them to increase dramatically. This saves vast amount of money on construction. 23% of aluminium is used in construction. The Empire State Building was the world's first skyscraper to use the material extensively. Its corrosion resistance and lightness made it the perfect material for external framing and roofing. It's clear to see, without this material the world we see today would be very different, and only recently has aluminium started to see competition from composite materials like carbon reinforced plastics, but that's a topic for another day. Thanks for watching. This video was sponsored by the Vlogbrothers. I didn't even have to put this message at the end, but I don't believe in getting something for nothing, so please go check out SciShow's latest video, The Physics of the Roller Coaster, and consider subscribing. If you have any questions, feel free to ask in the comments, and if you'd like to support this channel, the links for my Patreon, Instagram, Facebook, and Twitter accounts are below.